الشبكة العالمية للعلماء الجزائريين إيناس هي منظمة غير ربحية تأسست عام 2016 من قبل أكاديميين ومهنيين جزائريين مقيمين في الولايات المتحدة الأمريكية. الهدف من وراء تأسيسها هو رد الجميل للوطن والمساعدة في رفع مستوى التعليم في الجزائر. مهمة إيناس هي ربط الكفاءات الجزائرية في جميع أنحاء العالم مع نظرائهم في الجزائر. من بين أنشطتها نظمت إيناس مؤتمراً مهماً عقد خارج العاصمة واشنطن في الولايات المتحدة الأمريكية عام 2019. حدد المشاركون في المؤتمر عدة قطاعات حيوية تحتاجها الجزائر، واتفقوا على العمل في 10 مشاريع تغطي مجالات مختلفة نذكر منها التعليم والرعاية الصحية والزراعة والسياحة البيئية إلى آخره. والعمل في هذه المشاريع لا زال قائما. تستخدم إيناس أكثر المناهج العلمية تطورا من أجل تسيير ومعالجة هذه المشاريع. البداية المتواضعة لإيناس تضمنت عددا قليلا من الأعضاء، وهي اليوم تضم مئات الجزائريين الأكفاء من جميع أنحاء العالم. هدفهم هو المشاركة في رد الجميل والمساهمة في بناء جزائرنا الجديدة. هذه الثلة من الكفاءات الجزائرية الفخورة بوطنها تجمع بين التنوع والخبرة مع الاستعداد والرغبة في تمهيد الطريق من أجل مستقبل مشرق للجزائر. تستخدم إيناس منصة تقنية جد متطورة تسمح للأعضاء بالتعاون وتبادل الأفكار والخبرات. كمنظمة قائمة، إيناس لديها أقسام عملية مختلفة تضمن الدعم المحترف لجميع أعضائها ومشاريعها وتظاهراتها العلمية. نرحب بكل الكفاءات الجزائرية في العالم للانضمام إلينا في هذه المهمة النبيلة. الجزائر أكبر منا جميعا، فلننهض ولنترك بصمتنا.
السلام عليكم، مرحبا بكم في الويبينار جديد لشبكة إيناس. دونك اليوم رانا في ويبينار جديد في الفيزيكس اكزاكتلي في الالكترونيكس اورجانيك الكترونكس باستضافة الدكتورة فاطمة بنشيخ من اليابان وبتقديم الأستاذ حمزة الأبيض. نخلي لك الكلمة.
السلام عليكم. Today we'll have a talk given by Dr. Fatima Bencheikh from Japan. She's an Algerian scientist in optoelectronics. She got an engineer degree in electronics from Mohammed Boudiaf University in Oran. Then she moved to Aix-Marseille University, where she completed a master's degree in micro and nano electronics. Then followed by a PhD in the same university where she worked on organic electronics. Now she is a co-founder of Qualitech company startup, and she is also a visiting associate professor in Kyushu University. So thank you, Fatima, for accepting our invitation. I think you can start now your talk, and it will be great if you can give a bit more in details your path in research and science. Maybe this can help to motivate and inspire young students. Thank you very much again.
Thank you, Hamza. Can you hear me?
Yes, we can hear you. Yeah, perfect.
Okay, sounds good. So شكرا حمزة على هذه الدعوة، وشكرا لإيناس. هذا عمل جميل اللي درتوه باسكو احنا ça nous permet de voilà كما قلتوا نردوا للجزائر الخير اللي درتوا فينا. دونك اليوم غادي نتكلم على les technologies nouvelles dans l'organique électronique. Donc je vais parler en anglais. So today's topic is about emerging technologies in organic electronics. So now I'm visiting associate professor at Kyushu University, but my main job is CTO at Qualitech. It's a new startup company, and you will discover this company in my presentation today. So So now I am in Kyushu University. So Kyushu University is in the south of Japan. So this university is the biggest one in Kyushu Island. So it was founded like in 1903, and it's ranked fourth university in Japan. And there's like around 18,000 students, where 6% are international students. So it's like a beautiful area. The campus is like surrounded by mountains. It's like on a seaside. It's like heaven, let's say. So, and as you may know, Japan has a very marked 4 seasons, and you can enjoy a very nice landscape in this island. So I really, really enjoy living here. So, okay, let's move to talk about science. So this is like a summary of my education and professional background. So I was grown up in Algeria and in Oran especially. I did my electronic engineer degree in USTO, Université des Sciences et de la Technologie Mohamed Boudiaf. Then I worked like for 1 year as a tutor in mathematics. And then I moved to work as an engineer and the maintenance workshop manager at Samsung. There was like a franchise in Algeria, and I worked like with a very beautiful team where I learned a lot about human resource, about management and leadership. And then after 3 years working at this company, I decided to move to France to do my research. Because I was very, very passionate about research, and it was like one of the biggest goals of my life. So I moved to France, where I did a master research in nanoelectronic devices. So why I did a master degree after an engineer degree? I didn't need actually to do the master degree, but it was completely different from what I did before. It's like more focus on physics. So I was thinking like, if I will do it, it will be complementary to my first engineer degree in electronics. So yeah, I was motivated to learn like something new, to learn more about physics, because as you may know, nanoelectronic devices, we use a lot of physical laws, and then it's very important like to know these laws. So I studied and worked very hard, as to be like a top class and to have a scholarship. Let's say to have a PhD scholarship. So I got one which was between laboratory and also industry. It was mainly focused on the fabrication and characterization of organic solar cells. So as you can see here, those solar cells was meant to be flexible, transparent, semi-transparent, let's say, and also colorful. So it was a very nice journey. I worked with industrials and also with universities, and it was it was a very, very nice experience. So I got my PhD in Aix-Marseille University at the Institute of Material and Nanoscience of Provence. There was a very, very nice environment and a very, very good team. And during my PhD, I did also like, I teach like physics and electronics. It was also a nice experience because it allows me to see whether I want to stay in academia or go to industry. So after that, after like 5 years studying in France, I wanted to change the environment and go to another country, discover like new research in my field. So I chose like to go to Japan. So why Japan? Because there was like a good laboratory in organic light emitting diode, which is quite different. So organic solar cell, you absorb the light and you generate electricity. In Japan, I worked like this. The mechanism was the inverse. You put some electricity, you polarize the device, and then you get light. So it was for me, it was like not something completely new, but let's say another application. So it was like nice to discover new application. So I worked like 3 years in this lab where I worked on OLED and also organic laser. It was a new field for me. So I had to learn about optics, lasers. It was also new thing to learn, but as I love learning new things, so it was like very challenging and also satisfying for me. So I did like 3 years postdoc. It was successful. We got many papers and many patents. And then we were like, why not creating a startup company? So I was hesitating between going to academia or going to industry. So finally, with the co-founder of Koalatech, I decided to start this adventure to create a startup company. And as you may know, startup company is like a small baby company. So you will do research and development at the same time. So it's not like that much far from research. So I was like, yeah, why not? Let's try. So now I'm very happy with it. So from 2019 up to now, I'm working as a CTO in Koalatech. So during my postdoc in Japan, I had like many. I worked with other laboratories in Australia, in China, and in UK, and it was like a very fruitful collaboration. So I learned a lot of new things. I get to used to know new people with new fields. So it was a very nice opportunity actually. Okay, so today I'm going to talk about organic electronics. So my background is like organic solar cell, organic light emitting diode. So you will hear the word organic many times in this presentation. So we will see what happened when electronics meet physics and organic chemistry. So let me just bring the pointer. Where is the pointer option? Automatic highlight. Laser pointer. Here we go. Okay, so when you mix electronic with physics, with organic chemistry, you get something new, which is organic electronics. It means you will use organic material to do some electronics. Let's see what is organic electronics. So it's always easy to define something by comparison to another thing. So especially if this field is like new to some people. So let's say what we know is organic, is conventional electronics, is what you have in your TV, in your laptop, in your phones, you know, is silicon-based electronics. So this electronic is very nice. We can do many things with it, but there are some limitations. It's bulky, it's thick, it's rigid, it's opaque. The fabrication cost is high, but actually there was like a lot of investment, and now the cost is low. But let's say if we look at the real cost, in the beginning it was quite high, and there's also a high environmental impact. So this electronic is good, is nice, but we cannot just continue with electronics. We need another thing complementary. So here we have organic electronics. So organic electronics is, let's say, an exotic electronics. So it can be flexible because we use some molecules, polymers, and it allows us to have a flexible device, transparent. We can make these devices using solution process, and then we can use a printable, low fabrication cost technique to produce this kind of devices. So let's take a look to these molecules here that we use for this electronics. Please remember that in conventional electronics, we use crystals. In organic electronics, we use molecules. And this makes a huge difference between these two electronics. Okay, now let's go like deep down to the physics a little bit. So here, this is these three names are very, very famous in the organic electronics. So in organic electronics, we need materials, and these materials are organic semiconductors. So these three guys here, Iger, Magda Yamrid, and Shirakawa, they discovered a high conductivity in a doped polyacetylene. So polyacetylene is a polymer. So it's a carbon-hydrogen chain. This is why we say we call this material organic materials, because it's composed of carbon and hydrogen. And this discovery, they could get the Nobel Prize in 2000 in chemistry. So you can say, why with chemistry we can do electronics? So yes, this material are like chemicals that we can synthesize. The guys in organic chemistry can synthesize these materials, but with these materials we can do some electronics. Why? Because there's some electronic properties which allow this material to be conductive. Not very, very conductive, but let's say this semiconductor, they have a conductivity which is between insulator and metal. This is why we call them semiconductors. So this here, the comparison between these two materials, you have the crystalline semiconductor, let's say silicon, for example, and then we have organic semiconductor. One of the famous one is the anthracene. So this silicon, for example, if you take the example of silicon, you have a strong covalent tie between atoms. The atoms are strongly bound. In the case of organic semiconductor, you will have atoms inside one molecule, but one molecule and another molecule, you don't have a strong connection between, let's say, strong bonding between these molecules. You will have a weak van der Waals interaction. So it's electrostatic interaction. So here there's like a very weak bonding between these two materials, two molecules. So here the charge are delocalized. So this is why we can have high mobilities. In the organic semiconductors, the charge carrier and exciton are very localized. This is why you can have a high charge carrier mobility in the case of silicon and other inorganic semiconductor. But for organic semiconductor, the charge mobility is low. So why these transport properties are different? So here when we say delocalized, it means that if you take an electron and this electron can move freely in your structure. If you have like a lattice vibration, what we call phonon, heat, this electron will just be scattered when it meets a lattice like deformation or something like this. But still here, you will have a high mobility. What happens when you increase the temperature in this material? So actually, when you increase the temperature, the mobility drop, meaning this electron will not move freely. In the case of organic semiconductor, they are amorphous, so we don't have a band transport, we will have a hoping transport. Here we say that charge carrier are localized due to the defect or the disorder. And here, for example, this electron can move and then stay here, blocked here. And if we have a lattice vibration, what happens? We can release this electron. It means if we increase the temperature, we can give some energy to this electron to jump to another high energy level. And in this case, in these materials, when we increase the temperature, the mobility increases. So the behavior is different. We have a high mobility, but it can decrease with the temperature. Here, we have a low mobility, but this mobility can increase with the temperature. Okay, so this inorganic material have a low absorption coefficient. So you need to have a very thick material in order to absorb light. In this organic semiconductor, actually you need just few hundred nanometer to absorb light. So this is why we use thin films in the case of organic semiconductor, and we can make flexible device So I will talk about this later. Here you have these materials when we want to fabricate a device. If you want to fabricate diode or transistor, actually they have a high melting and sublimation temperature. So you need to use a high temperature fabrication process. While for the organic semiconductor, they have a low melting and sublimation temperature. So you don't need to go that much high temperature as for the inorganic semiconductor. So in the case of the inorganic semiconductor, you have high mechanical strength and low compressibility. So it's a little bit hard to make flexible device, even though for some compound, when you mix some materials, you can have like thin films, and thus you can have flexible materials. But in the case of organic semiconductors, like polymers, plastic materials, they have a low mechanical strength and high compressibility. So you can make flexible device actually. So here we can see that for these two technologies, the physics and the manufacture process is very different. So in my case, in my career, I studied this semiconductor in USTO in Oran. But when I moved to France, I studied more about organic semiconductor because it was like exciting subject. The physics was different, the properties were different, and this was like very challenging for me. But I was like, okay, let's take this challenge and see what will happen. Okay, so you will in inorganic semiconductor, we have a very low exciton binding energy. We will see what exciton mean. But so you will not hear a lot talking about exciton actually. In organic semiconductor, you will hear talking a lot about exciton because exciton exists. We can, let's say it has a high binding energy. This is why we can hear a lot about excitons. So now let's move to just a small explanation about what does exciton mean. So exciton is just you take an electron and a hole, like positive and negative charge. You bring these two charges together, like near to each other, and then these two charges, they will be attracted to each other by an electrostatic Coulomb force. And this new particle, we call it exciton. So actually it's a electrically neutral quasi-particle that exists in insulators, semiconductors, and also in some liquids. So the properties of these excitons is like the energy, the binding energy, the lifetime. It does have a lifetime. This exciton cannot live eternally. And also a diffusion length. It means this exciton can move, and then these are like recombine or just separate. That's what we call a diffusion length. So what we can do many materials actually using molecules. Here you can use, you can ask chemists to make many type of materials. And nowadays, people are more interested in AI because the possibility are infinite to make molecules. So this is why it is useful to do some machine learning AI for molecular design. So actually, with these molecules, we can design fluorescent, phosphorescent emitter. We can have optical absorber and charge transport material. It means we can make OLED, we can make lasers. Here we can make solar cells, and for charge transport material, you can just make some wires to transport electricity. So you can do some electronic with these materials. Okay, so now let's move to the applications. What are the applications of organic electronics? So the most famous one, I think, to people is like organic solar cell, but I would say OLED, because OLED is a compound which has already reached the market. So people who have the latest smartphone, some brands, they already embedded an OLED display. And this OLED display, now you can find it like in many places. Like you can see here, this is Seoul airports. They have like a huge display. There's like small displays connected to each other. And these displays are made of organic light emitting materials. You can make flexible, you can even use in automotive, and also you can have a nice design for like home appliance. Also here you have solar cells. I did my PhD, I fabricated organic solar cells. So solar cells, as I said, you absorb light and then you generate electricity. And then you can also make sensors. There's already some proof of concept in University of Texas and also University of Tokyo. So you can have like some displays. You can have also some antenna or some sensors, skin mountable sensors. We will see this application in the end of my presentation. You can also make some organic field effect transistor, and also you can make organic memories. So of course, some of this application does not reach the market yet, but it's ongoing. So about organic solar cells. So this is like the proof of concept, and some products are already commercialized. So you can make like flexible solar cells, and here you have some fancy prototypes. You can make some decoration, and there's also like prototype of cars with solar cells. So these solar cells are very light, so you can actually embedded them in many many applications. Like, so if you are interested about solar cells and you would like to see the efficiencies, I advise you to take a look to the NREL website. This website show the records of the solar cell, and each color here show a solar cell with some materials. So you will have like in purple multi-junction cells using inorganic semiconductor like gallium arsenide. In blue, you will have like the crystalline silicon solar cells. In green, thin film technologies. And then in red, you will have organic and hybrid, what we call immersion photovoltaic application. So this immersion technology started in the 2000, and now, as you can see, there's a nice increase of the efficiency. So today we are talking about organic solar cell. So let's focus on organic solar cells. Let's take a look at the efficiency. So here recently, organic solar cell could achieve 18% efficiency, which is quite nice. It's similar to the amorphous silicon based solar cells. So that's, of course, this is at research level, but actually there's many companies in Europe and in China and also in other countries where they are trying to commercialize this technology. So when I was doing my PhD, the efficiency was, I think, around 14%. And I fabricated like some organic solar cells in collaboration with one laboratory in Marseille. And we could achieve 7%, which was, I think, not very bad efficiency. So what is organic solar cells? So it is a stack of thin films. So here, please focus only on this layer, active layer. This layer is responsible for the photoconversion. It means you absorb photon and you convert this photon into electricity. So this active layer, here we call a bulk heterojunction. It means we will mix two molecules. One is a polymer, for example, and one is a small molecules. You can have also two small molecules, two polymers, but the most famous one are polymer for the donors and small molecule for the acceptors. So for people who are like familiar with the semiconductor, physics of semiconductor, you can just say this is type N and type P. It's like you will have a junction, PN junction. So you mix these two material and you make this layer here, which is responsible for the conversion. So this layer have high absorption. Do you remember I talked about organic material? I said they have a high absorption coefficient. It means you don't need to have a very thick layer to absorb light. So that's why they are interesting. So actually, if you take a look to what happened inside this solar cell, so there will be like light coming from the sun. Your device will absorb this light and then create what we call an exciton. Exciton is electron, positive, negative charge bounded. So we create excitons. These excitons will move. And this exciton will move. And when the exciton is near to the NP junction, like to a different energy level, here you have a separation of positive and negative charge, and this is how you create electricity. Here I simplify a lot, but let's just keep this in mind. And then if you want to dig more about this, you can find like a lot of paper and books talking about the detail of this process. So this is how you create electricity in an organic solar cells. This, during my PhD thesis, I mainly worked on the morphology of the active layer. So I just changed it like the temperature and see how the properties of the film is changed. I did also some simulation modeling in order to see how to improve the efficiency. So we could improve the efficiency from 4% to 7%. And also, interestingly, we could get a colorful solar cells. So it was a very, very nice experience working with all these guys here. So if you're interested, please take a look at these papers. Okay, what is interesting in solar cell is that organic solar cell is that, as I said, they can be flexible. So in this case, you can use some roll-to-roll technique, inkjet printing to produce kilometers of solar cells. So this is also a very, very interesting advantage in organic solar cells. Okay, next, I will move to the second topic, which is related to light emitting device. And this is my second experience, which was in Japan from 2016 to 2019. And it was the subject of my postdoctoral fellowship. So I started working with OLED. I worked also with transistors and then with organic solar cells. And I was like very keen to work with all these different devices because I was like, yeah, if one day we want to make all organic electronic platform, I want to be part of this project. So yeah, that's why I was like very, very excited about this project. So here you can see this like OLED that I fabricated. So the amazing thing with light emitting device is like when you fabricate and then you polarize with electricity, you can see the light, and this is very, very satisfying. So actually, here we are talking about light. So let me just talk about some history of lighting. So light was like, we know, was invented like long time before with the fire, and then there was lamps. You have like the fluorescent lamp, you have incandescent lamp, and then along the time, this way of lighting was improved, and we discovered LED in 1962. We got the first red light emitting diode, and then to move from one color to another, actually we waited like 10 years, and then there was orange, yellow, and green light emitting diode. So please keep in mind that this light emitting diode is made with inorganic, it's not organic semiconductor, okay? And then there was like in 1978, we have like the blue LED. So we waited long time to move from one color to another. What is interesting with organic semiconductor is that the first demonstration was in 1963. So it was the first demonstration of an organic light emitting diode. I will say OLED from now. But this demonstration was like this OLED, to polarize this OLED, you need 400 volts. So no one want to buy this kind of OLED. So you need to make some improvement in order to lower this voltage. So in 1987, there was like the green OLED, which was there was like many chemistry, organic chemistry, material development, and the green OLED was demonstrated. And then just after the green OLED, followed by all the color, like blue, red. So this is also one of the most interesting things in organic semiconductor, is by doing organic chemistry, which is quite easy synthesis, you can move from one color to another just by designing different kind of molecules. Of course, you need to have to take care about many properties, but it was like much more easier compared to the conventional materials. So after that, we moved from like a lighting to a new word, like displays. So we were using these small lamps inside like a matrix, and we call these pixels, and then we can construct images. And this is the displays technology. So here you have Sony's first OLED TV demonstration, and then also there was like many fancy demonstrations and prototypes, like Audi TT. Here you have a coating of the car with OLEDs. Here you have demonstration of a semi-transparent TV, and then you can see that you have many objects you can wear, and that include this OLEDs. So here I just put this one because this is from Kyushu University, the lab where I'm working. So it's like a demonstration of a flexible device, and this flexible device, they can also be used in lighting and also in flexible devices. So in the future, we are thinking also about new fancy applications like smart windows, transparent phone or transparent device, also large area lighting, and why not biocompatible e-skin? It means some device that you can wear on your skin to monitor your health or to do other things. So here you are free to imagine what do you want. Okay, so what is organic light emitting diode? So as I said, it's the inverse of solar cell. So actually you inject charge, this charge recombine, and then you get light. And this light will propagate inside your OLED, and some of this light can be outcoupled from the outside, what you get here. So of course, here I am simplifying a lot. There are a lot of problems and a lot of challenges, but this is just a simple picture, like to more just popularize this technology. So I worked in this topic with some people, and we had many interesting research, and we published it in Nature, and it was like a very nice journey, because I have to work with chemists, to talk with chemists, and to learn about chemistry. So it was very nice. So I was in charge of the simulation device design, and here chemists actually, they can make N-type, P-type semiconductor, and based on this material, there is the recombination zone where we create the light. The position can be different. And because this position is different in your device, actually you can increase the efficiency. So here, please focus only on the red part. When you generate light near to the metal, for example, here, you will have 9% of efficiency. While when you shift this recombination zone to the other side by using an N-type material, it means you design new molecules here, and then this recombination zone shift to the semi-transparent electrode, and then you can increase the efficiency to almost 20%, so almost double. So this work was done in collaboration with Saikun, and it was a very nice research. Also, we worked on thick OLED. So before OLED was a thin layer. So thin layer, you have interference. And when you have interference, when you change the angle of a view, you can see different color or the quality will be degraded. So the challenge was, can we make a thick OLED? And it was not like easy because the mobility is low. And if you make a thin film, actually, you will degrade the electrical properties. So here, the idea from Matsushima, the guy I collaborate with, working in the same laboratory, he used a perovskite. It's a hybrid semiconductor. So he used a perovskite layer, and then I did some simulation, some modeling, and then we could demonstrate that using a thick OLED, we can have an emission which is not dependent on the angle of a view. It means you can see the same quality at different angles, and that was a very, very good discovery, and it was high impact, so we could publish in Nature and we could get patents. Okay, now I will move to the lasers. So we can also make laser with organic material. So before, lasers were like big crystals, and then we have to wait until 1977. There was the first demonstration of the VCSEL, which is a vertical cavity surface emitting laser. And then now in your smartphone, for people who have the face recognition stuff, you have a near infrared laser, and that laser is based off a VCSEL. So it's used for face recognition, for many object recognition system. So here I put the picture of Professor Iga Kenichi, who was the first inventor of the VCSEL. And actually, I had the chance to work in Kyushu University in one project where he was a supervisor. So we got a very, very good advice actually from him to develop the new generation of lasers. So finally, we could, in 2017, achieve the world's first demonstration of organic semiconductor laser by electrical injection. And then from that, we decided to found a startup company. So here, this is just the details that you can find here in papers for those who are interested. I'm not going through details here. It's, I think I gave too much detail today. So then we co-founded Qualatech with here Adachi Chihaya, who was my boss during my postdoc. He was my supervisor, a very, very famous person in the OLED community. He was a very good mentor for me. And actually, he's a very amazing guy who has a huge imagination and solution solving, problem solving. So it was a very nice opportunity to work with him. So with Adachi Chihaya, Jean-Charles Ribière, he's a French, and Takashi Fujihara, we co-founded Qualatech. So in Qualatech, we are aiming to develop lasers for sensing application like face authentication or iris, fingerprint. We would like also to focus on, in the future, on healthcare, and then other system here, for example, transportation system. You know, when you have a self-driving car, automatic car, you need many sensors. And in this case, lasers can be very, very important. And also for education, AR, VR, and also head-mounted display. And why not in the future, including sensor in some display and windows, smart windows. So, okay, let's now just go to see what is the future of this application. So I think everyone is familiar with now connected devices and also health monitoring sensing device like the watch that you wear, and it can monitor your heartbeat or other function of your body. So in this case, these devices are bulky. Now I think we are satisfied with this kind of things, but in the future maybe we'll be looking for more non-bulky device like electronic skin patch for health monitoring. So here you can have just a very thin patch, and it can be like skin wearable, and it will improve, I think, the life of a patient who cannot always wear some devices in hospitals or other things. We can also think about like multispectral biometric authentication. So here there is already one prototype by PhotoNation. So you can have like iris recognition, but the problem with this one is that it uses a near infrared light, and we cannot catch all the detail about the iris. So you need visible light actually to have more rich sensing of the pigmentation and also to excite the melanin. So in order to improve the biometric authentication system, we need to develop different colors of lasers and OLED in order to catch more information about biometric compounds. Okay, we can also use in light. We can also go for healthcare and beauty. Actually, our skin can absorb light, but the depth of the absorption of the light depend on the wavelength. It means depend on the color. If you have a UV or blue light, only superficial skin can absorb this light. And then if you want to go deep inside, so here you increase the wavelength. If you use a near infrared, you can go deeper, and it depends on what you want to do. Actually, you can select the wavelength and treat whatever you want, like skin disease, or just like go for beauty, like laser skin rejuvenation or other things. So this is not like just a dream. This is already like there's already some prototypes, as you can see here. There's like a flexible, patchable, stretchable device that you can, this is just a demonstration, but let's say that in the future, we can see this kind of stuff. Okay, now display and AR VR. So light is also important in this application because you will have a projection in your retina or just on a screen near to your eye. And this, you need three colors, as you may know. If you want to make a display, you need red, green, and blue. So if you use OLED, the spectrum is large. If you use laser, the spectrum is very narrow. So you can have extremely high purity, color purity. You can have also high brightness. It means that also you don't need to use a lot of optics to focus the light, because it's more easy to work with laser rather than OLED or LED emission. So yeah, this is like one of the future application, I would say. For the head-mounted display, it already exists. There are some prototypes, but in the future, yeah, we can see like more small devices and fancy one. Okay, this is like more, I think, fundamental science, but I was very, very interested about this one because this is using laser. You can design the cavity. So in laser, you need a cavity. You need a resonator. So by designing a nanostructure here with this shape, like a vortex, you can create a vortex beam. And with this vortex beam, you can in the future make 3D display, and you can do some microscopy application, improve the microscopy applications, and you can also use it for information carrier for visible light communication. So this is just a published paper. So people who are like interested, you can check this reference. It was just published recently. So, and this is just a prospect of what would be the application of a vortex organic laser. Okay, so now I would like just to finish the presentation by summarizing my scientific and professional zigzag, I would call it zigzag career, because I didn't have like a linear career. So I did research in optoelectronics. I went to private sector where I worked mainly on management and maintenance in electronics. And then after that, I was driven by my dream, which was doing research. So, and then I moved to France. I did like research in nanoelectronics, where I discovered organic electronics. So I was very keen about these new topics. And then I moved to Japan and worked hard on this field. And then I just like had the like what would be the next challenge. So for me, was creating a startup was like a very challenging thing. So I was like, yeah, why not? I was very afraid in the beginning, but I was like, okay, let's try it and let's see. So now I'm like in a startup doing some research and development, and also doing research with Kyushu University, and a lot of development in the startup, and I really enjoy it. Okay, so this is just the things I learned in the startup. So in research, of course, we learn a lot of amazing things, but what motivates me in a startup company is how we can try new idea actually about making a company, because all the companies does not have the same philosophy. And when you make something from scratch, actually you are free to do it your style. And that's what I really like it on making the startup company. Okay, so I think this is the end. I will skip this one, and then I will just acknowledge all the funding, all my supervisors in France, in Japan, and also Kuala Tech people and investors. And thank you for your attention.
Thank you very much, Dr. Fatima. It was so nice presentation, so informative as well. And it was also so impressive. So good to see the importance of multidisciplinary science, especially. We could see how physics, chemistry, and electronics meet to found new science and technologies. So it's so good and also impressive what you did in research and also development. Now we can start questions. We have a first question here is how expensive are these new devices compared to the classic ones? For example, OLEDs versus normal LEDs.
So I would say in the beginning of each technology, it can be expensive, but if you compare like the price of the materials, the price of the fabrication process, OLED fabrication process is very cheap. I cannot give a number, but it's much more cheaper. You can say like, but OLED display, the price is high actually now. The thing is that before there was like a lot of investment, there's a lot of companies making LED LCD, so they could decrease the price with years because they get benefit, and they could use their machine many times and then decrease the price. But if you just compare the price of the machine and the process and the materials, I would say OLED technology or organic technologies are very cheap. I don't have a number, but I think it's just what I can say. It's like very cheap, cheaper than than LED or LCD.
Okay. We have another question here. So, how can we make analytical instruments cheaper and easy to use by Algerians?
How we can make analytical instruments more cheap and easy to use by Algerians. So actually some of the process are like cheap, but cheap, if it's hard to say, but I would say like what Algerian can do in the organic electronic field is to synthesize a fancy molecules. So organic chemistry, I think it's not very expensive to do some organic chemistry. We have a lot of laboratories of chemistry in Algeria. And then now the most expensive things, not only in money, but also in time, is to make efficient organic semiconductors. And if organic chemists people can focus on making a very, very good molecules with a very good properties, and I think they can sell these molecules very expensive. Because in Taiwan, please take a look to the Sigma Aldrich, Merck company, and the Lumtech in Taiwan. You can take a look at what they are selling and how much they are selling polymers and small molecules. So you can get a lot. You can, I think, have a lot of money, and just by synthesizing molecules.
Regarding that, actually, did we really reach the low fabrication costs of electronic, of organic electronic devices, especially when we know that the process of making these devices, well, the synthesizing molecules maybe is not extremely expensive, but the process of characterization, optimization, and all this, when we know also all the techniques coming with the thin layer deposition, they're not really very cheap.
Yes, actually, yes. Even if you synthesize the molecule, you need a spectroscopy measurement system. And I think in some countries, there are also like some laboratories where they are not rich. In some countries, not all the countries has like a fancy laboratories, but they have a platforms. So I think if you are not obliged to buy expensive equipment for each laboratory, you can make like a platform, and then chemists can make their molecule in their lab and then move to that platform to do all the characterization. Okay. So spectroscopy is like UV visible spectrometer, FTIR. Of course, it costs money, but I think by creating platforms, I think we can like reduce the cost, because we don't need all these things in one laboratory. In France, they have like 2 or 3 instruments, and then if you want to do some expensive characterization, you have to go to some platforms.
Okay, if we can make, for example, a list in a platform, a list of techniques that should contain, for example, these techniques, what kind of techniques, for example, they should bring, or
Okay, I see. So spectroscopy, the most important one is the UV absorption, transmission, and reflection of light, like UV visible spectrophotometers. You can have like fluorescent meter, like equipment which can record the fluorescent spectrum or phosphorescent spectrum. And then you can have also NMR. So NMR is quite expensive, I think. It's, I think, the most expensive one. If you make a chemical compounds, so you need to know what are the constituents of this compound. So you do need NMR. This is like the main one, which can be like a little bit expensive.
We can use FTIR also to
yes.
Some ideas about.
Yeah. Yes, exactly. Yes.
Okay. Okay, let's see another question. Okay, we have another question here.
هل تتم بعض التجارب لهذه المواد في مسارات؟
I don't know what he means by مسرعات. Whether
Les accélérateurs, I think he's talking about accelerators, like in incubator or something like this. هل تتم بعض التجارب لهذه المواد في المسرعات الموجودة في اليابان؟ So yes, there are some platforms, and if you need to do some experiments that you do not have, you can do just a collaboration with other laboratories which has the equipment. So you make a proposal together, and then you can have a collaboration. It's not like not everyone has like this access to the accelerators. Accelerators are more focused for startups if you want to commercialize your product. But if you are in research, you will do some collaborations, and mainly collaboration, I would say.
this is a bit technical. I don't know the
TTF. What do you mean by TTF? Like Fourier transform?
I don't know. I have no idea about this. Okay, so let's see other questions. Maybe this is the comments or other.
Just a second, I will just move this here. So I mean, the new technology now is quantum dots matching QLED with OLED by Samsung. Yes, actually, yes, there's like a quantum dot. So they use like nanoparticles. It means the emitting material is nanoparticle, quantum dots. So what is the question? I mean, the new technology now is QLED. Yes.
I think it's kind of comments. Okay. Yeah.
So yes, I confirm. Yes.
Yeah, okay. We have other questions. So please do not hesitate to ask any question you have in mind. It's really an exceptional opportunity. So
I could read some comments from the comments. There's like yes, that one. I was reading this one. Which field we classify the organic electronics? Yeah, that's a good question. So there's a problem with classifications actually. Organic electronics is a cross field. So now it is electronic. But you will find many chemistry laboratory in the world making the high impact work in organic electronics because they make new material. So yeah, now it's like organic chemistry and electronics. So it's in between.
It's kind of material science.
Yes, mainly yes.
Okay, we have another question here.
If I'm working with a laboratory in Algeria, I'm not working, but just having like discussions sometimes. But I don't have any like official collaboration.
Okay.
So there's one question: هل تستعمل المواد التربة النادرة في مشاريعكم? So it's like earth, rare earth, like ytterbium, So yes, I'm not I didn't work on this topic like directly, but I had some colleagues who worked with the ytterbium compound, and there are some molecules, organic molecules, where you can put an atom, an earth rare atom, and you actually they have a very amazing, they have an amazing properties. So it's a very interesting topic. So yes, you can use this kind of materials in organic electronic.
I think this question is has been answered previously.
I see.
All of these science.
Mm-hmm.
In your opinion, it is easy to develop this science in our country. And, I don't know which side they mean. Maybe the parts you did is not really the synthesizing the molecules. Maybe the other parts.
Okay.
You already answered kind of. You by founding this kind of platforms to do things.
So yes. Yeah, actually, I know that in Algeria there are a lot of people who can do amazing work in calculation and modeling, and I would say that now the hot topic in organic electronics is to do some like AI to design molecules. So it's like computer aided molecular design. It means that the computer will help you to find the best configuration of the molecule that you have to synthesize. Because if you synthesize 1 million molecule, it takes time to synthesize 1 million and to get maybe 100 best molecules. But if you do some modeling and use it, and also you use some AI, actually you can win time and you can develop a strategy on how to make a very good molecules. So in a pharmaceutical field, they already use this kind of algorithm to find the new medicine. So they are very well developed, but in the organic electronics, not yet. So I would recommend people to take a look at this kind of things, because this is like the future of the organic electronics, because you can have a lot of patents. So the IP, you can dominate everything, and you can also propose and sell your idea like as a consulting company. So if it is expensive to buy equipment, it's okay. You don't need, actually. You can sell idea. That's, I think, the most fruitful business nowadays.
يعني تركيز على ماذا نحسن صنعه، يعني واش اللي عندنا كما كان يقول في البروفيسور بالقاسم حبة the last week.
Exactly.
We have another question here. Can a new startup in Algeria jump directly to organic electronics?
If we yes, as I said, the last idea, if there will be a startup, it will be more on like material design, new material, new properties. So it will be like using just an idea. It's like using machine learning, artificial intelligence to do some molecular design, and then design few materials which has amazing properties, and then sell these materials to Samsung and LG. So just these two customer, you need to seduce just these two customer, actually.
Very interesting. Okay. So can scientists in biology and can be involved in the field of organic electronics?
Scientists in biology, can they be involved in the field of organic electronics? Yes, definitely. Yes, actually, there's like one paper on living organic laser. So in jellyfish, they could discover, like in jellyfish tissue, there's some molecules which can emit laser if you excite with an external light source, and then you put this tissue on a resonator, you can get laser. So this is one amazing thing. So yeah, you can, there's like in USA, there's like many people working on very interesting topics in biology, where they think about putting some implant in the brain, or in just like in human tissue, to catch some electrical signals. So yes, there's room, I think, for biology in organic electronics.
I have another question. You founded a startup on your providing organic lasers. What kind of difference or maybe what kind of characteristics of these lasers in terms of maybe spectral properties and other properties compared to standard lasers?
Okay, so standard lasers, you have the blue laser, the green, the red, and the near infrared. These are different technologies. The green, for example, the blue laser, you use gallium nitride, and you have your experimental fabrication process machine, and there's one company which make the blue. For example, in Japan, they have Nichia. Nichia can make the blue because they have the fabrication machine to make the blue. If you want to make another color, you have to buy or build another experimental machines. So if you take a look at the near or the red laser, you will find Panasonic. So Panasonic, because they work with arsenic, aluminium, arsenic, and arsenide, gallium. So it's different compounds. So in this case, if you move from one color to another, the technology change, the equipment change, everything change. In organic electronics, you can make all the possible colors in the spectrum, from 400 to the near infrared. Little bit limited nowadays. You cannot go more than like 900. It's a little bit hard to go more than 900 nanometer, but you can do it from 400 to 900 by fine-tuning the wavelengths in a nanometer scale, which is amazing. This is something very hard to do in organic laser, in conventional laser.
Because they are organic, in terms of the spectral property, we know that organic have several very narrow energies. So they are known by wide shape in terms of the energy, the wavelength, or maybe the purity of the colors. So are they really well kind of single mode? Not really single mode, but are they really narrow enough to give very good purity, color purity?
Yeah, that's a very good observation. Actually, yes, organic material are amorphous, so the spectrum is broad, emission or absorption is broad. But if some material has gain, if you put this material in a cavity, so this cavity will narrow down your spectrum, same as for inorganic laser. And then with the laser, you can have the high purity, even though with amorphous material.
Okay, that's interesting.
Is it possible to use e-skin on bionic arms? Yeah, why not? Please, yes, I think, yeah, it's possible. هل بدأتم في البيكو؟ No, not yet. Nano, so nanometer, you know, you are approaching the atom size. So pico, you have to ask maybe a nuclear physicist, maybe Hamza.
Okay, I think we read no more the questions. So many people are thanking you for the great presentation.
You're welcome, guys. Thanks. Oh, simple. Thank you. I tried to make it simple, but I was a little bit doubting, like, maybe it's complicated.
It was really, really informative and very kind of, yeah, we could grasp information quite easily. So
that's nice to know. Oh, Shaima is here. Hello, Shaima.
What kind of, if you have to give some kind of advice to young students still, for example, studying in bachelor, in licence, what we call licence, what kind of advices you give them, for example, if they want, for example, to pursue their career in organic or in optoelectronics, your field mainly?
So
kind of advices, the path, the skills.
So in general, it's hard to talk. I can talk in particular, like to electronic people or to chemists, but I prefer to talk in general, and then after we can go to particular specific things. So I think the advice I can give, like, to students, the first important one is the personal drive. You have to find what will drive you. It is hard. It's not easy. Maybe some people are lucky to find it like easily, but I was not lucky. So I worked hard on like overthinking and trying to figure out what I want, what I like to do, what I really, really like, to make like my personal life and my career, make them converge. It was a little bit hard, but when you are in a quest, when you are searching something, you will always end up by finding something interesting. Maybe you will not find always what you planned in the beginning, but you will find sometimes something more interesting and more beautiful than what you planned. So I would say like personal drive, like, hard work, persistence, motivation for success. You want to success in one project, you have to get the motivation. If you start by saying I'm not gonna succeed, it's hard to succeed when you think you will not succeed. So believe on yourself, try to find passionate work and make all your energy on it. Intellectual curiosity is very, very important. Make clear things. If you don't understand things, ask questions, read, ask questions, and then don't skip it. Focus is very important. It was because I think many students, including me, I had problems on focusing. I like to study many different things. I like to try many different things. And then at the end, I find myself like I couldn't focus on one thing. I couldn't make one thing perfect. So focus is very important. Try to just like do not disperse a lot. It's good sometimes to disperse, but you have to control this dispersion. Disperse a little bit, 10%, but focus 90% on one thing. Then I would say education and career background, it's very important also to choose where you want to study, where you want to go to study. Not always we can choose, but at least just think about it. And surround yourself by, I think, by good people, good mentor, good friends, because there is like one social study was amazing. it said like we are the average of the 5 people that are surrounding us. So I think be careful about your environment. Not be careful like I don't talk with this guy. No, you like science, surround yourself by scientific people, because it will be more easy to ask them questions, to get motivation, to see where they fail, so you can learn things from them actually. And I'm not saying this like only scientists. You can go for artists, you can talk with artist people, they have also very creative mind. So yeah, so if we go for more specific thing like electronic and chemistry, so for electronics I would say like there is very amazing things are in the nano electronics, micro and nano electronics. And if you don't have equipment to make I don't know, fancy device, you can focus on the physics, but don't do the physics of the old physics. Stop doing like inorganic semiconductor, I would say. Do new things, quantum dot, quantum mechanics now is very interesting physics. So I would say it's very interesting, yeah, to go for quantum, because now many applications start already to use quantum phenomena, like optical computer, quantum qubit, and all this stuff. So take a look to the new things. Go to the website of the big universities in your field and check what they are doing. Email them, ask them questions. Be like always in action.
Nice. Very valuable advices indeed.
For chemists, definitely organic chemistry is now it is one of the most valuable job in Asia, in Europe. They are looking a lot from organic chemists. There are big companies like Merck in Germany, in China, also many like DuPont, Dow. They all do chemistry. And chemistry, because material, everything now, the price is decided by the material. You can decrease the price of the device, but if your material is expensive, you can never decrease the price of the product. So find a new material with amazing properties. You can have high efficiency, and then this material will be cheaper, and then you can sell a huge amount of this material, and this is how you can make your profit. In science or in money, it depends what do you want. For online labs. Okay, that's a very good question. And so physics simulation. So actually it depends on the phenomena you're using, but there's a lot of open source softwares. If you're doing ab initio, if you're doing DFT calculation, if you want to work on small molecules, dynamic of molecules, or just if you want to make the best organic semiconductor, you can find many open source softwares. For example, for DFT calculation, for chemists who are interested, I think the one I used like long time ago was Siesta. It's an open source. Go to the open source websites and you will find like Siesta. There's like platforms like this. You just need to be in Linux mode, so you can find the interesting things. For device simulation, it's more like there are commercial software, but actually you can make your own software using MATLAB or Python. So using Python, you can find many also free softwares. People who want to work with organic solar cell or OLED, please check like Harvard or big universities. They have open source codes that you can just like take and then modify and improve. So you can participate to their platform, or you can just like keep it for yourself or sell it, or. But you have to check the copyright, of course. You can use quantum yes, quantum espresso. Yes, exactly. Yeah, for DFT calculation and quantum mechanics stuff, you can use also quantum espresso.
Do we have other questions?
There's like one question is like, are there international universities that receive PhD students in mechanical of materials? You mean I could understand. Okay. So yes, of course, there's many universities. You have just to check the laboratory which is doing the topic you are targeting, and just please contact them, email them. Maybe the mechanical properties of material, I think.
I think that's what he means.
Yes, of course. These kind of things are in the heart of many let's say industry. If you go for plane industry, for boat, ship industry, they are interested about the mechanical properties. So you can find this in mechanical engineering department of universities. Mechanical engineering, yeah. Mechanical or material engineering, material science. Selma, by the way. Hello, thank you.
So we have any other question? Let's wait a minute to have possibly another question. And I just want to remind that Dr. Fatima is very kind and very generous, because now the time in Japan is around midnight, and she's making this only for you, to give you the science, the information about the science and technology of tomorrow. So take this opportunity to take the most of it.
With pleasure. That's thanks.
Yeah, thank you very much. A huge thanks again.
You're welcome.
I think we don't have any more questions, so we can probably end the event of today. So thank you again, Fatima. It was great honor, and with great pleasure we had you today. So hopefully we will have you again, possibly in another, to talk maybe about another patents, or maybe other impressive research that you are doing, maybe in another topic, another date, inshallah. So thank you again,
inshallah,
and see you guys in the next events.
Okay.
Assalamu alaikum.
Thank you very much, Hamza, and thank Ines for organizing this nice event. Thank you very much. Thank you all.
The International Network of Algerian Scientists, INAS, is a nonprofit organization founded in 2016 by Algerian academics and professionals residing in the USA. The motivation is